Hey guys, how's it going? Welcome back to the channel. This week I actually wanted to do something a little bit different. I know I've been talking about hillsides lately, and this is actually leading into a case study that I really want to go through with you because it kind of encompasses all the factors of hillside stabilization. But I briefly mentioned in one of my last videos the retaining wall underneath the hillside, right? So if you got a hillside here, you got to put a retaining wall in generally. Now you can do things like vegetation and so on and so forth, stabilize slope over here and creep zone or whatever. But you have to remember that granular materials create both axial and lateral forces, right? That's both down and out. So typically speaking, if you're going to build a structure here and you want to stop this hillside from collapsing over onto it or prevent landslides, all that fun stuff, or you know, you've got hillside here and a retaining wall to retain all of the soil back here. So a couple things about that. Granular materials create both axial and lateral forces, right? So if I've got a hillside, right, I'm just going to put a footing L shape here like that right now. A couple things to note is that the shallower you are to the surface, the less that it's going to be pushing on the lateral forces are going to be pushing on the retaining wall, right? So if I were to represent the forces with an arrow, a short arrow is like smaller forces, and then you'd have larger forces and larger forces, right? And that's what it would look like. So up by the surface, you'd have some force laterally, you'd have more force laterally, you'd have more force laterally, right? So pushing onto this retaining wall yonder, and then the lower you go, the more force that you have, right? And that's an important concept for what we're going to go through. Now, a little bit about what we're making here, guys. This information that I'm pulling is actually from an engineering model that was done, or a model that was done with marbles and a simulated retaining wall. This was actually done by a YouTube channel called Engineering Models. They have really good information on there, not just about retaining walls, but about loading, about basically just different engineering principles. Very easy thing to watch, and a very educational. I strongly encourage you to check them out on YouTube. Once again, they're called Engineering Models. Their logo is basically a big circle, and it's all black, and it says in white block lettering, Engineering Models, like so, right? That's the guys. You should definitely check them out. Matter of fact, most of what I'm talking about right now is exactly what I wanted to talk about when I made the last video, and I said I'd address it later. And then I stumbled across this company, or this YouTuber, I guess, called Engineering Models, and I found them in the ASCE's civil engineering group on LinkedIn. So kind of really cool connections and really great visual representation of everything that I'm going to talk about today. Anyway, going into it. So when you design a retaining wall, right, and I was mentioning before, you need to have as-built drawings as to what this retaining wall looks like. Is it an let's see, hillside there, right? Is it an L shape that goes in toward the hillside? Is it an L shape that goes away from it? Is it a T? Like what is this, and what's sort of the better means and methods to do it, right? Because that's going to change the approach. Okay, so there's a couple of different types of failures that you have when you have these types of things. Which one is the better model? So, oops, wrong one first. Again, I'm just kind of emulating their experiment here, doing it here without the actual model. But really good information. So when you design a retaining wall, right, and you have those forces being applied, 1, 2, 3, you have to figure, like, how do you support this? Now, at first glance, if I were to do this direction, right, into the hillside, they have a failure called overturning, right? And overturning is when you apply enough force that this thing falls over. And you can imagine if this is freestanding and there's no load supporting it or whatever, this is chilling, this falls over super easy, right? Because there's no support on this side. It falls over super easy. So the overturning point, it is right there, thing collapses, and then in the video they show that you just breathe on it and it falls over. So at first glance, you would think the better support would be an L shape away from the hillside, right? Because it would resist that overturning moment that you have there. But I should grab a couple different colors just to help out. And it will resist that overturning force, right? You can imagine you apply pressure up top. This resists that overturning motion by resisting the downward force here, and that works, right? But what you end up noticing is, hey, sorry, somebody was at the door, my fault. Anyway, so you have this overturning moment, is what it's called. I'll get over that in a second. But what they do is they end up filling this box back here. What they do is they have this whole box, and as they fill it with marbles, when the marbles hit down the bottom here, what you realize is there's a second mode of failure called sliding. So it's when the retaining wall doesn't tip over, but the whole thing just kind of slides, right? Because you can imagine these forces are pushing on it, and if the friction gives way here, then this will actually slide on the soil. Now, the engineers who design the retaining walls can either design this so that it's deeper and helps resist that sliding, or they can put like a geomaterial down at the bottom to increase the skin friction. So they do this test, right? And in this test, the basic premise of it is to have your footing, and then they actually have both ways eventually. But now let's do two separate ones. 1, 2. Now what we're going to imagine is this box, right? And the same thing. And what they end up doing in this experiment is they start filling it with marbles, right? Which creates those forces, right, that we were talking about. And as they fill it up, they get this slide. And in this experiment that they were doing, they were measuring how many centimeters tall they could get the marbles into this guy. Missed it. They can get these marbles into this guy. And when it was just free alone without the geomaterial or friction mat simulation thing, what they eventually got was 3 centimeters of height of marbles before they experienced a sliding failure of this model retaining wall. So afterward, they came back and they put the geomaterial simulation down at the bottom here to help increase the skin friction of the bottom of the retaining wall, prevent the sliding forces. When they did so, they were able to continue filling this, right, until they had about 8 centimeters tall, and then they experienced the overturning failure that you would have seen. Now, when they did the retaining wall pointed the other direction though, and they popped in these marbles, right, they were able to get this guy 11 centimeters, which means that the L-shaped retaining wall that goes back into the hillside with the skin friction of the geomaterials down on the bottom, or geogrid, or whatever fiber mesh that they're planning on using in order to increase that skin friction, resists the most amount of lateral forces. Why is that? There's 2 reasons. Oh, my drawings still suck. Eventually, my drawings are going to get better. We're just not there yet. So, you got your L shapes, right? First of all, the forces that you have to resist that strengthens it, is the weight of the concrete or the top of the retaining wall all pushing down to the bottom of the retaining wall, right? So that's one of the forces that helps kind of anchor this guy in place. The second force is your friction resistance, right, which we increase with the geomaterials down on bottom, but that helps you prevent the sliding that you were experiencing, okay? So why does the L shape that points into the hillside resist better than one that points away from the hillside? And the reason is, when you put the soil in there, instead of just having these forces as my resisting forces, when you pop the soil on, you also have passive pressures pushing down on this wall. Well, that weight translates to further weight down into the soil, right? And by pushing down on something that's connected on the L shape, much like this resists the overturning, right? This prevents this motion. This is also going to anchor down with all these passive forces resisting this overturning motion. And by putting more weight down on where you have the friction here, the friction force, the more weight you have on that, the better the friction resistance that you're going to have, especially with the geomaterial and blah, blah, blah. So all of the additional weight of the soil that you're retaining up here actually helps support this entire wall, right? So when an engineer is designing a retaining wall, finally did it, I screwed up. Anyway, so when an engineer is designing a retaining wall, okay, what they're imagining is the moment of failure at this point right here. And again, to quote engineering models, they call this point Q. And they're imagining how much of this pressure, this lateral soils pressure, right, creates the overturning. And they call this overturning, when this thing rolls backward, they call this overturning a moment, which we label as MO, right? So they try to find how much of this lateral pressure creates the overturning moment and calculate all of it. In kind, they're also calculating how much of this passive pressure down on the footing is the stabilization moment, which they label as the other way, MS. And essentially, they're making sure that this stabilizing moment is greater or equal to the overturning moment. And they do that by extending the footing further and further, right, until all of the soil forces here resist that overturning moment. So if I'm designing a hillside project and I have absolutely no idea what's going on here, you have to be careful about things like injection grouting or something like that, because if this is short, or especially if this retaining wall was designed backwards, which we've determined shouldn't, but maybe it is, and you inject grout here, which increases the lateral pressure on this retaining wall, you could create a sliding moment and push this whole thing out, right? If you're doing tieback anchors, where you put a wall plate here or an I-beam or something, and you run through with your anchors, right? And then when you tension it, you try to pull this thing back up. But if you have a footing down here and soil or anything has gotten in here, that's going to help resist the straightening moment, right? In kind, if you've got soil over here, that's going to help resist that too. So these are really, really good repairs, but it's impossible to figure out what type of failure you're experiencing without knowing what exactly you're looking at on a retaining wall. So looking at the face of a retaining wall, that's grade right here. You know, you can pop, you can pop that I-beam on there, right? With soil nails or tieback anchors in there, and from the side view, that looks like little threads, boom, anchors here, right? In order to tie that and pull and straighten this guy up. That's one very, very common repair. Now, depending on what type of failure you're seeing on top, if you are seeing an overturning moment, this retaining wall here, let me change colors again. If you're seeing an overturning, this retaining wall will tilt yonder, this direction, which means it looks more like that, right? What that looks like on top could be, or well, what it looks like from the side is if I'm looking down at a retaining wall, I just see the whole thing like tilting out, right? That's overturning. That could be too much lateral earth pressure that's pushing onto the retaining wall. It could be insufficient retaining wall design. It could be the footing was built wrong and it's just not enough and it's pushing the whole thing over. This is starting to help you generate what type of repairs you can do. If it's soil nails or tieback anchors or the wall plates with the tieback anchors to help like pull on this I-beam. I'm showing an I-beam, but it's wall plate, right? And they anchor that in, which pulls this direction, which can help straighten this retaining wall, right? Very, very good repair if we do something like that. If it's too much lateral earth pressure, you could do like a cellular concrete, but that adds a lot of weight down. A lot of weight down on top of that L-shaped footing, right? If I inject a bunch of concrete, lightweight concrete over here, that's pushing down on this. So I need to find a way to push down on the stabilizing section of the footing without pushing against or increasing the lateral earth pressure to create the overturning. Especially if this breaks, you're screwed, right? So that's another very real concern. Like, there's nothing you can do that's going to solve that. Now, if I were to do like a polymer injection, right? Hillside here, and then I do polymer injection underneath. What do we know about polymer? We know that it reduces lateral earth forces by approximately 40%, which takes some of that lateral pressure off of this, or any load that you have up here, right? If I've got a building, a structure, or if I've got anything up here that creates load down into the soil, it reduces that lateral earth pressure by approximately 40%. And if that helps take the pressure off of this retaining wall, reduces the lateral forces that are creating the overturning, then it's all good, right? If I look at the side of a retaining wall, and it looks like my belly right now. Anyway, right, let's say this is the earth. I can't see underneath. I don't know what kind of footing this guy has at all, right? But if I look at the retaining wall and it's starting to buckle, and it looks like I got a little belly sticking out. Usually has a crack right along that seam right there, right? Especially CMU walls or something like that. You know you're probably going to want to straighten it using those tie back anchors if you get a chance, right? That helps increase it. But you know what else helps straighten it up? If you're just starting to notice like if it's not this exaggerated, right? Let's just say somewhat like that. And I'm looking at a retaining wall, and by looking at the CMU blocks, I can see a crack running through it, but it's not quite pushing out. Carbon fiber reinforcement is a phenomenal repair for something like that. They pop those carbon fiber strips and it increases the lateral resistance and the strength of CMU or block walls. If you look at their website for like a Fortress carbon fiber strips, those lateral testing that they did increased it by something like, I don't know, it was something dumb. It was like 550%. Or maybe I'm thinking about the I don't know. But take a look at it, right? Those carbon fiber strips are a very, very good repair in order to increase the lateral strength or lateral resistance of the retaining wall and the overall strength of the CMU block wall. So sorry this one was this one was all over the place. I got really, really excited when I saw this testing and a lot of the information presented by engineering models. Once again, check them out on YouTube. Aside from that, you got any questions, comments, concerns? Please DM me or message me privately. Leave it in the comments or links below. Anything like that, please click like, subscribe, and all the stuff that is YouTube. Anyway, thank you so much, guys. Hope you have a great day.